Welcome back. So before the break, we did a little bit of an overview. So we looked at properties, we looked at types of forces, and we looked at representation. Now let's be a little bit more technical, okay? Let's get into the nitty-gritty of it. So what we're going to do is we're going to now talk about what happens when you push or pull an object, okay? So we're going to go to a bit of a simulation, which is great because I can't draw. So there we go. So here we have our little man, okay? And what we're going to do is we're going to start applying a force. Now here, I haven't got friction. We're ignoring friction for now because it's going to be a bit easier. And I want you to see the speed. So it's going to be a little speedometer. That's just going to show you how fast it's going to go. Watch. I apply force. It's not in fact, it's zero. Nothing's happening. He's not pushing, he's just standing there. Okay? Pushes a little bit. So we apply a little bit of a force, and you can see he starts moving. But can you see, if you look at the speed, he's getting faster and faster and faster. But he's pushing the object. Okay? If I make this force smaller, now his force is zero, it still keeps going, and it keeps going, and it keeps going, and it keeps going. It'll keep doing this. There's no friction. Now, hopefully, I can apply the force again. I apply the force, what happens? He starts to speed up again. So, if there wasn't a force at the beginning, so we're going to reset it, okay? At the beginning, object wasn't moving. Then we had to apply the force, okay, so we had to give it some value, and then the object could start moving. So we could speed it up. If I took the force away, it still keeps going. If I want to change the motion, I have to apply the force again and make it go faster. Okay? So the force did two things. Started it moving, and then it could make it go faster. But, there we go. But, that's only force in one direction. Let's play some tug of war, which is over there. Okay? We have our men. Let's put a speedometer. There we go. That's the word I'm thinking of. On our little object. There we go. So, I'm now going to put a man on the rope. Nothing's happening. Object is stationary. Now we're going to let him pull. So it's like tension. This force is a tension force. There we go. And he pulls. What do we see? The force, let's pause it. The force is to the left, and the object moves to the left. So instead of going to the right, like we saw in the first one, now it's going to the left. Okay? Let's put a force on the other side. Let's see if we can change the object's motion. So we could see, if I just leave this here, it was getting faster and faster. Okay? Now, let's put another man. Now he's the same size. So what the animation is trying to show you is because the guys are the same size man has the same size force. Okay, so that's important. Now watch, and I'm hoping he doesn't go off the screen completely. Oh, and if you look there, oops, he had to stop. Now this is quite important. They went for a while, and then it stopped. Why did it stop? Here's another force. So this little block over here is a force. It stopped it. So it was moving, then it stopped. Okay? Let's start again. Now we have them, equal forces on both sides. Watch what happens. Oh, look. Nothing. The forces are equal, so we're experiencing a force, but there's no change in the motion. Let's make the red guys more heavier. There we go. So the force, now they're going to go to the right. I've stopped it. Now I've got enough time for you to see. There's the speed, okay? I'm going to put another one here. Equal forces on both sides now, okay? Just like right at the beginning. But it was already moving, so what happens here? Now the speed doesn't change. The speed stays the same. Still moving though. So the forces are being experienced, so what we've done is we've changed the motion. It was getting faster towards the right. Now it's going the same speed towards the right. It's not getting any slower or faster. I'm going to put one more. Now I'm putting a big guy on the left. Let's see what happens. It slows down, stops. Did you see that? It slowed down, stopped, and now it's changed direction altogether. Okay? So what did we do with what this has shown us? The force can start it moving, the force can make it go faster, and the force can make it go slower. So those are the things the force can do. This animation unfortunately doesn't show me the other things, so let's go there. Okay, so we're still on properties. We've done this, we did that earlier. So over here, what can a force do? A force can cause an object to start moving. We showed that. It can make an object slow down, speed up, or stop. And these are all good things. It can also make it change direction. Now that we saw when it slowed down, remember with the two, when we had the nice big blue one, it slowed it down, it stopped, and then it changed direction. It doesn't always have to be horizontal. It's like when you're driving in a car and you turn the corner. You've changed direction, you've applied a force to the wheels. It can also change a shape. Like when you were little and you played with Play-Doh and you squished things and stretched things and changed shapes. That's all forces. It can also cause an object to rotate. As in a car, when we put the force on the wheels turn. That's rotating, okay? Or if you're playing cricket, spin bowlers, they make, with the way they bowl, they make the ball spin, which is important, so it's rotating. So we can do all of these things with the force. You've done that before. Okay, so let's do some questions just to make sure we're on the right track, okay? I want to draw a force diagram of a person pushing a box to the right. We're not going to worry about the person, but what I want is I want all the forces that are acting on the box. So now we're going to have to think a little bit, okay? So, force diagram means we have to have a box. We have our box. Person is pushing it to the right, so we've got to remember which way is right. It's that way. Okay, that would be a basic diagram, but we know that there's going to be gravity. Gravity goes from the center down. Okay, we know there's going to be the normal force, which goes up like that. I didn't tell you whether there would be friction or not. Okay, so you need to be careful with questions like this. Don't make an assumption about something. So here I'm saying just draw a person pushing the box to the right. Don't assume there's friction. In your exams and tests, they'll always be specific. Okay, yes, there's friction, no, there isn't. Sometimes we ignore friction because it makes life easier. So we're going to ignore it for now. But I never leave a diagram like this. I've got to label it. So this is my normal force. F with an N. This is gravity, Fg. And this is my applied force, my pushing force. Okay? We usually put a key because there's different ways that we can write these symbols, which you may have seen. So Fn can also be written as just a capital N, and that's the normal force. So you may be using a capital N, you may be using Fn, it doesn't matter. But this is the normal, okay? Fg, which is weight, can also be written, now you need to be careful with this one, as a lowercase w. Okay, I don't like teaching my learners to use a W because sometimes it looks like a capital W, and capital W is work. It's a different thing altogether. So it's got to be little w, okay? And that's weight or gravity. Whoops. Then there's F. Here, you may sometimes see it as FA, so you might go F applied, but you need to be specific when we label this one. So this one, you can't just say it's an applied force. It is an applied force. But what we actually have to say is we have to say it's the pushing force. It's the box, it's the person pushing the box. Okay, so you need to describe to me what the applied force is. Where is it coming from? So here, I would put this as the pushing force. That's an I, by the way, pushing force. Okay, don't just say applied force. Why do we put the key? Because we can use different symbols. Okay, and all the symbols are right. We just got to make sure that whoever looks at our diagram is on the same page. Okay? All right. So, force diagram. Now I say to you, draw a free body diagram. What was the difference? We said right at the beginning, force diagram was the box. Free body diagram means a dot. I prefer free body diagrams. So here we have my dot, okay? The first two forces are easy because there's my normal, there's my gravity. Remember, I said when we draw forces, the size of the force is represented by the length of the arrow. So when we draw diagrams like this, if two forces have to be the same size, which these normally are, the normal and the gravity, we should draw them so they look like they're the same size. Your examiner is not going to take out a ruler and measure it, okay? But if it obviously doesn't look the same, then there's a problem. So just make sure they look like they're the same size. Now we've got to be careful, because we said there was a pushing force, and our temptation with a free body diagram is to draw it here because it's pushing. But free body diagram, the forces must be away from the dot. So what we've got to do is take this arrow and put it on the other side. Okay, so I'm going to take it out from there because that's wrong. Okay, and what we need to do is we need to draw it there. Now, the reason why we do free body diagrams is because when it comes to our calculations, these are actually more useful for us. So when it comes to us needing to find net force for Newton's second law a little bit later on, this is useful. When we just have them shown exactly where they all go on the boxes, we can get a little confused as to what goes where and what belongs where, and it gets complicated. This is just better, okay? So, we're going to take another little break, and then we'll do some questions.